Good morning, everybody. Welcome to the 15th European School on Computational Methods in Dosimetry, State-of-the-Art and Emerging Developments. Before we start, I have to say a few technical things. We have a part of the audience participating online. Therefore, if we come to questions and answers, please wait for the microphone to be passed to you so that the people online can also hear what you are saying. And now to the people participating online. You have in the big marker, you have two options to communicate. If you have scientific questions to the talks, please use the question and answers section, Q&A. If you have technical issues or with connections or just want to say hello to everybody, please use the chat. And Marianne is actually following the question and answers, and after the talks she will inform me, and we will then ask the questions so that you can also get the answers. We have a quite crowded program. Okay, so actually the original proposal made for this, for offering such a school was that within Working Group 6 we have had a series of intercomparisons in computational dosimetry, which will appear in a special issue of radiation measurements. Most of the articles have already been published, and the special issue is just in preparation. So the outline of the talk of the school is shown here. In the last column where you see an IC, that's actually on one of these intercomparisons, but we thought that the school should be a little bit more broad and general. So in the beginning we will have introductory talks by Paolo Ferrari on computational dosimetry in general, and introduction to Monte Carlo radiation transport simulations by Vladimir Markovic. Then there will be two talks from the intercomparison exercises, one by Carles Domingo on the neutron unfolding exercise, and one overview of all these exercises by Rick Tanner. After the coffee break, we will have three presentations from the field, from experts in the field. Manuel Bardies will introduce to us the OpenDose 3D project. And then we will have new developments in particle radiotherapy given by Emanuele Schifoni, and then talk about accelerating Monte Carlo simulations by Francesc Salvat. After lunch, Maria Sankel will report on one of these exercises, which was about implementing ICRP computational phantoms in different exposure scenarios. Then Pasquale Lombardo will actually talk about the new developments in computational phantoms, namely flexible computational phantoms. Then Robert Bernard will talk about data processing and radiation protection dosimetry. And the last talk by Habib Saidi will actually show the emerging role of artificial intelligence particularly in internal radiation dosimetry, but it's definitely a topic that is on the rise. So thank you very much for attending this school. It's quite well attended, given that we had a long dinner yesterday. And I hope you enjoy this school. And to the speakers, please be aware that the time slot you have is 30 minutes, and it should also allow 5 minutes for questions, if possible. All right, so did I forget anything? No. So we start with Paolo. Could you switch? Okay, there, it's coming up. So you use this microphone.
Okay. These two.
These two, yeah. Mm-hmm. More or less pointing.
Okay. Thank you. Thank you very much. Good morning, everyone. It's an honor for me to have the first lesson for the introduction of this very interesting school, and I have to thank the committee, and of course Jose Maria Gomez Rosa should have here, but he could not come, so he prepared the majority of these slides that you will see in a moment. So let me start in a quite pedantic way, I can say just from the definition, but this gave give me the opportunity to also to cite Bernd Siebert. That was one, because yesterday we see the history of EURADOS, and Bernd Siebert was one of the main component of WG6, so the computational part. And in this paper, he just give a definition of computational dosimetry that is a subdiscipline of computational physics devoted to radiation metrology. So it seems quite a small part of an intersection of three main areas that are physics, math, and computational science. But a second definition is quite more challenging, because it said, is taken from the same paper. Computational dosimetry may be defined as the process of connected and ordering of known data by means of relation based on theory and established models in order to create new data and to reveal new insight. So this is something more challenging, because we are producing new knowledge, sometimes also new physics, maybe and considering high energy physics, when this kind of stuffs are used continuously. Computational dosimetry can be divided in some subgroups. So you can have analytical method, you can have deterministic method, and of course Monte Carlo methods that are fundamental in for to determine radiological quantities and to simulate complex geometry, because we see that with analytical methods it's quite difficult to have a really three-dimensional complex geometry. With the analytical method you can solve, for example, many simple cases, and this is very important because it can be used also as a validation of other method. For example, if you take, for example, a source, a point-like source, you can easily determine in a very simple case with monoenergetic source, a point source, the flux in a certain region of your space. And so you can compute the doses just multiplying with a very simple formula. So you can determine the flux at this point, and or if you put in something inside between the source and your detector, your detection region, your tiling region, can be also the hair, so the attenuation. You can easily somehow determine this attenuation with a normal decay law, and in simplified and good geometry, you can arrive to this simplification of your system. In other cases, you can, for example, have the situation in which you want to compute the emission from a surface. So also in this case, you can use this kind of a formula. In this case, you have also the build-up factor that takes into account they are not in good geometry, so there is the build-up of the radiation inside the different kinds of material put between the source and your detector. And you arrive to this kind of formula in which you have to integrate this kind of exponential that cannot be solved analytically. And so you have numerical data and numerical tools in order to determine your solution. Another quite interesting and simple method is all these methods are called somehow point kernel method. And one interesting application is for the line source, for example, in case of the searing or the pipeline, which you have a radionuclide. So in this case, you can use a very simple scenario in order to determine the flux in a certain point, and with the flux you can determine the dose rate. And we don't need to go inside the calculation, but this is just important to remember, to remind that in these cases the attenuation is 1 over the distance, and you can use it for your calculation. This is quite important for each kind of source, that can line and not point source. So it's quite important because it's one of the pillars of radiation protection, the distance as the time and the shielding. For more complex sources, also in this case, you can have point kernel sources taken from a quite old book, the Engineering Compendium Radiation Shielding, but more or less the formula is the same. So they are tabulated values, or the Sievert integral, for example, another integral cannot be solved analytically, but you have tabulated values, you have curves, and you can solve, for example, some of this kind of problem in which you have a rectangular surface source in case of contamination, for example, or decontamination in this case. Or you have some scraps or some deposition inside your pipe in case of a facility in which you have some radionuclide inside a flux of water or vapor or something like this. Or cylindrical source in which, for example, for the waste or for the beaker used for the nuclear medicine. Deterministic method can be used, for example, to solve a more complex and general problem. If you want to define your radiation transport in general inside your space and your phase space, because you have the position, but you have also the energy of different particles, you can use the Boltzmann transport equation. It was not solved by Boltzmann for the radiation, of course, it was solved by the kinetic theory of the gases, but the situation is very similar from the point of view of the transport. You think of small molecules, and they're very similar to a small particle, we can say. And in this case, you want to determine the number of particles in a certain volume, in a certain part of your general your geometry. So you define a volume, and in this volume you want to calculate the number of particles that are present at a certain time and the variation. Take into account that the flux can be expressed as the multiplication of the number of particles in volume and the velocity of this particle. You can rearrange this formula, this equation, but I was saying, to express your flux and to use it in somehow to solve your transport problem. It's a balance equation because you have to determine the production term, the absorption term, and the leakage term from your volume you are defined. This is the representation of the formula. Trust me, that is the representation. And you have, okay, I cannot point because the pointer does not work here. But in the integral, you have the so-called in-scatter term. So that is the part of the particle, the number of particles that do not belong originally to your volume, but that because they scatter outside, go inside. So you have a number of particles that are increasing in your volume. The S is the source term that can be or not be present in your volume. And the other term, one is the absorption, and the term with the gradient is the leakage term, so the particles that are escaping. Of course, this kind of formula in this general form cannot be solved analytically. You have to make some cut on energy, on dimension. For example, you can consider a one-dimensional problem, and for example, one infinite cylinders is the case of reactors, for example, and some kind of reactors, of course. Or you can use a different kind of technique to tackle this kind of problem. One is the finite element methods, and you see this nice picture taken from ITER, and in which you go and determine a solution in a number of points belonging to this net. You see this ramification, the net in which you try to find the solution, and you increase the number of points in the critical point of your geometry. Or you can use the finite difference method, in which somehow you come back to the original definition of derivative and integrals. Derivatives are just the ratio between differences between the variables, and the integral is just a sum of something. Of course, with the fluence, you can have also the vector energy fluence, and of course, when you have the fluence, you can compute the absorbed dose. These are just some links to deterministic code. You can go in there and find them. Another kind of way to solve your problem, to face, better saying, your problem of radiation transport is using Monte Carlo simulation. Okay, Monte Carlo simulation we use here for the radiation protection, radiation transport, but of course it's a general technique, can be used for different kind of problem, from the weather forecast to the economic and so on. So it's just a tool, we can say. Here are some link to computer code, to Monte Carlo code, and you can go. Of course, some of them are free. You can be licensed to use them, and these are some characteristics. Some of them are multi-purpose code. Some of them were originally thought for a particular application, or are particular efficient in some kind of application, or some treats only some kind of radiation. So depending on the problem you have to tackle, you can adjust, or better, you can try to find the better code that suits to your problems. One of the main characteristics of the Monte Carlo code is that you really can treat geometries. So saying geometries means part of the reality vary from a very small structure like the DNA molecule to the large facility as ITER, passing through. You can see here the application in medical physics. In the corner there is the head of LINAC for the treatment of for radiation therapy treatment, and for example, the representation for the body here is an intercomparison of used to calibrate the whole body counter. So you can see how really the geometry can be defined in a very detailed way, and so you can, knowing the reality at this level allows you to get a solution really in a very specific point, in a very efficient way. The ingredients, we will probably see better in the next presentation, but the ingredients of the Monte Carlo simulation are few, and they're very simple, we can say. We worked on the fact that the radiation transport is based on a series of interaction. A series of interaction that belong to a history of one particle. So step by step, you can compute the different interactions that happen to the particle. It's based on the fact that if you can produce a lot of particles, you can base your solution on the central limit theorem that guarantees you that the convergence of the mean to the real value or expected value of the real population. So on the random number generator, because you need a random number generator. This is the core of the Monte Carlo simulation, and of course, for the physics, you need the data libraries. This is the main important thing, that you need data libraries for your simulate your interaction section, because till now you have not a physical part. I mean, there is not physics in the first three steps. With the Monte Carlo, you do not solve really the radiation transport solution, but really you try to simulate what's happening in the reality in your medium. So here is just an example, for example, of photon attenuation in water or electron attenuation in water, just to give you some view. And okay. The next one, you see the number of interactions that you have. For example, for 10, this is just a simulation of the tracking of a particle inside a volume of water. And you can see here the photon is the blue one, and the photon inside the water, the number of interactions that has about 20 collision, okay? Compared to what happened to the electron that seeing the Colombian forces has many more interaction inside the same volume of water. In order to simulate the interaction of photon, you have a very simple way to follow. Because if you came back to the definition of the attenuation, okay, of the photon inside a certain volume of material, you can see that this ratio gives you somehow the surviving beam fraction, okay? So the 1 minus the rest is the fraction that probabilistically has interacted with your volume, with your material. And if you extract a number, random number between 0 and 1 from your random number generator and put equal to this part of the equation, you can assume that the probability of being absorbed is given by this number, just for chance, just by chance. If you invert this equation, this is possible to invert it, you can find the position in which this possible interaction happened. So the next point is only to ask to yourself, considering your geometry, if this interaction point is inside or outside the material, because if it is outside, that means that this interaction could not happen inside the material, so you have not the interaction, and the particle just passes through. If the interaction is inside, you have to ask yourself what's happening, which kind of interaction, depending on the energy, depending on the material and the cross-section. So this is but probably you will see better after. This is just to give you an hint on what is the base of the Monte Carlo simulation. This is for the photons. For the electron is a little more complex because you have to divide, because you have seen the number of interactions that electron has in a very small part of their track inside a material. So generally, not for all the code, but generally is divided in sub-step and is used some approximation, for example, in MCMP, for example, the code that I used, the continuous slowing down approximation, in which you consider that this pattern of sub-steps of the written track. I've said about fluence, and one possible estimator of the fluence is not from the direct definition, the number of particles traversing a surface, but you can use the sum of the lengths of the particle inside the volume and then make the ratio, so make the fraction in order to compute the fluence. Dimensionally is the same and is more useful from a point of view, more efficient, we can say, from a point of view of Monte Carlo simulation. I talked about the geometries, and as a matter of fact, you can treat different kind of geometry also with the new Monte Carlo code, passing from the voxel geometry that more or less similar to the Lego bricks, so you can, and it's quite simple to create this kind of geometry. The complexity is medium, but the tracking is very easy because just the Monte Carlo has to compute each side by each voxel what's happening, as we've seen before. Some Monte Carlo code can treat, of course, the meshes, in which case you have tetrahedra, and it's a little more complex. Of course, the accuracy of the geometry is better with respect to the voxel geometry. The tracking is a little more complex. The new kind of deformable geometry with the NURBS, in which you have a three-dimensional spline, are more complex from the point of view of definition. The accuracy, of course, is the best between this kind of representation, but the tracking is, I don't know if it is already solved. I presume it's quite difficult because of the definition itself of this kind of tool. Here you have just an example of the quality of the accuracy of you can get in representation, and the fact that with the NURBS you can make easily the deformation, for example, of your model. Generally now you can use the NURBS to create your model and voxelize it to allow the tracking inside the Monte Carlo. But otherwise, the deformation with the voxel is not possible because the voxel are just Lego brick, and so you cannot have angles as seen in the picture. Monte Carlo have been used, for example, for computational dosimetry to calculate the conversion coefficient for the operational quantity and the limiting quantity. Here, to give you just an example, is just the quantity, the effective dose and the equivalent dose in various organ, and you see how it is calculated. You take the ICRP reference phantom in this case, and you hit the phantom by an extended aligned parallel beam in void, and so you get the energy deposition through the tracking inside different organs, and so you can calculate the conversion coefficient. This is quite easy as a calculation. And the same was done in the past also for the operational quantity H*10 and HP10, but using not the voxel phantom, but because in the past, this is the publication ICRU 57, ICRP 74, the sphere, the ICRU sphere to calculate the H*10, and even if HP10 is defined in the body, it was used a slab of ICRU to compute HP10 conversion coefficient for monoenergetic energy. Now, the new operational quantity published in ICRU 95, just to give you the complete picture, has been calculated numerically employing the conversion coefficient published by ICRP using the voxel phantom. So you have the direct correlation between the operational quantities now, the new operational quantity, and the effective dose. This is the last slide, so I hope I finished in time. We've seen, okay, Monte Carlo is very nice. It can be used for different geometry, complex geometry. One of the main, you can say, characteristic, and don't say problem, it's not nice. The main characteristic is the fact, we have said that if I can manage to simulate a large number of particles from the central limit theorem, I know that the mean of the solution I got converge to the real quantity. The problem, so, is related to the uncertainty, so, of this mean, and the fact that you can see here that the relative uncertainty. So, if you divide the variance by the mean, you get a figure that goes as 1 over the square of n, and n is the number of particles. That means that you want to increase, to reduce to an half your uncertainty, you have to compute 4 times the particle, or to compute for 4 times, in order of CPU time, your calculation. And this is, okay, can be done for very simple cases, but for example, for very complex cases for deep penetration, in case of shielding, large shielding, this is a very, very big problem. And in this case, we have no time. You use some biasing of your calculation that is renormalized at the end and allows you to reduce the computational time, getting anyway a better uncertainty. So that's all. Here are some references to Monte Carlo and transport, and that's all. That's it. Thank you very much for your attention.
Thank you very much, Paolo, for giving this very nice introduction, which was actually linking to some of the presentations that we will have in this school. Are there any questions in the audience? Sorry, yes.
Hi, more than a question, it's a comment. When you were introducing the Monte Carlo codes, you talk about Fluka, but that's a bit obsolete information because Fluka had a fork in 2019. Now there are 2 Fluka. One is distributed by CERN, whose website is fluka.cern, and the other one is distributed by INFN, whose website is not up yet. There is still the old website up. Just that.
Thank you very much.
Yes, and to complete on that comment, of course, for EGS there are even more family members.
There is one request from the chat. Someone wanted to have the first line about Monte Carlo seen again. Is it possible to show again the first slide for Monte Carlo, please?
know if it is.
On the presentation.
Okay.
Ah, okay.
The Monte Carlo. Here, this one.
A GSC, oh, sorry. I have to repeat, okay. There is also a comment from Wolf Behrens that a GS NRC was missing in the list of the codes.
Okay.
Okay. Perhaps we have to amend that before we
We
put that
will
online.
amend. me and Jose Maria, we will amend also. Thank you.
Okay. Oh, there's another one over here. Not loud enough.
Okay. So thank you, it was very nice overview. My question is about this NARBS description. I didn't got if there was any attempt to insert this in Monte Carlo, because to my awareness, no. No, it is not. Okay.
I suppose till now there are no still no code that can treat this kind of because from the geometry they are very nice, of course, but it's very difficult because it is related on the point that you can make the elongation of these curves. So
Based on splines, no?
yeah, yes,
so
on three-dimensional spline. So
it's really okay.
it's not so easy to thinking that to the code to say, okay, this spline is which is the region that defining this spline, if you can modify it so in this way. So, in my opinion, there are no attempt till now. But
Thank you.
Okay, then thank you very much, Paolo. And we move on to the next presentation given by Vladimir Markovic, who has his own timer, which is very well appreciated.
Fulfill the real time. Well, hello to everybody. My presentation is about Monte Carlo radiation transport simulations, and here I'm not going to talk about Monte Carlo transport codes, but how simulation is really done. So we will get insight into a principle of simulation, how can be done it using computer in some general manner. So if you try to see what is Monte Carlo, you will get to a problem because there is no particular definition about it. You'll see that is some way of solving problems using random numbers. But that's very general, so you cannot know anything from that. But in principle, Monte Carlo can be used to solve either deterministic or either stochastic problems. So let's see insight into one simple example of Monte Carlo. This is the first example you will find if you look some textbooks or internet, how not to calculate. Monte Carlo has a problem, it cannot calculate anything. It can just estimate things. So using Monte Carlo method, we can estimate number of pi with some degree of uncertainty. So to do that, let's present some simple, it can be derived as a physical experiment. Take a cardboard, draw a circle inside of it, put it on the floor, take a full hands of grains of rice, for example, draw it, and that's the way to use Monte Carlo to estimate P. How can that be done? Well, count the grains of rices inside of whole rectangular, in square and in circle, and that ratio will give you the number of P. How? Because you know mathematics to see the ratio between surface of the sphere of the surface of the square and a circle, and you know that the probability for grains of rice to fall into the circle is proportional to that ratio, and you can estimate the number of pi. So here I need to emphasize another thing. In order to get better estimate of number of pi, the more number of grains you need. But there is also another method. You can do it once and then repeat it, do it again and again and again, and you get a lot of different values on number pi. Find the mean of it, and you will get some more even better results. So the ancient history of Monte Carlo is referred to a problem which Buffon, Conte de Buffon introduced in 18th century, and it was a problem similar to this one. And almost 100 years after that, Laplace suggested that this could be also used for determining the number of pi. Fathers of today's Monte Carlo transport codes are referred to be some great scientists, and there are two groups of them. On one side, Neumann, Ulam, and Metropolis did this, let's say, created in the way we know it today, the Monte Carlo method for transport radiation, and they tried to solve problem of neutron fluxes. Fermi did that also I think over a decade more before them, but he didn't publish any results. So these are the fathers of let's say, Monte Carlo codes that we know, methods that we know as they are today. They use first computers to solve their problems, and it is interesting thing that Fermi, because he didn't have the commissioning of first computer for solving Monte Carlo problems called ENIAC, and that computer needs to be moved somewhere else, and Fermi devised analog device for computer simulation. He called it Fermiac, and this is this wooden piece in the right corner, and if you take this and put it on a piece of paper, you can draw tracks of neutrons. He devised it for slow and fast neutrons. So let's get insight into a Monte Carlo. How can we transport radiation? To do that, I will give you a very simple example. To start from scratch, let's try to simulate one Brownian-like particle in equidistant steps and try to move it in a plane. So that's a pretty simple problem, and we will see now does it have easy solution. To do that, we need first mathematics. We need to define our problem, we need to define our reference frame, and then we need to start to have some starting or initial values. There should be some random point in this rectangle, and how can we derive random point? For that, we need to have something that we call random number generator. Random number generator, let us call for now some function that generates randomly number from 0 to 1 uniformly. And we will see later how that function works, but let us now suppose that we have that function and we call it, just simply state rand, and you get a random number from 0 to 1. How can we solve this problem? Well, if you see, point in the plane can be simplified in a manner that you can generate separately x and epsilon coordinate. If you had a random number from 0 to 1, you can easily extend it to some, it is intuitively clear how can you do that. Take a random number, multiply it with the length of your size of rectangular, and you get x and epsilon random coordinate. Okay, that's for a start. What are we going to do next? We need to move that particle in some arbitrary direction. How are we going to do that? Well, arbitrary direction can be sampled as some random point, in this case, since we are in the plane, on some circle. If we can somehow generate random point on the circle, that could be our next point of movement of our particle. How to do that? Well, let's change the reference view, go to the polar coordinate system, because the equations are simpler there, because it is reduced only to one-dimensional problem. You need rho is equal to d, and you only need to know the value of the angle phi. And phi goes from interval from 0 to 2 pi, and again, it is pretty intuitive. How can we derive that? Multiple random number generator with 2 pi, and you get some sample value from 0 to 2 pi. And if we do that, we get next point of our random movement of particle. Now, what is the next step? repeat it. Repeat it again as many times as you want, and you will get the track of particles. If you do the repetitions from the start again using another set of random numbers, you'll get another track of the particle. And if you do that many times, you can then extract some, let's say, relevant properties or relevant things you want to calculate. To continue, so we need to know some mathematics. We need to know what is the probability and what is random number variable, and how can we sample random number variable from any probability density distribution. I will not go inside to the details because these are part of the mathematics problem, but let's say if you know probability distribution function, then you know everything about that random variable. What is the probability density function? Well, it is the probability of occurrences of some random number in some very small interval. And if you know that, you know pretty much everything, because you can derive mean, you can derive variance, and everything else. Here is the example of uniform distribution, which might be a most important distribution in Monte Carlo simulations, because any distribution can be derived using this one. How can we do that? Well, first we need to introduce something that we call cumulative distribution, which is defined as integral in the first line. And this distribution has some properties that always grows, and it is in interval from 0 to 1. And if you take some simple mathematical derivation, you will find that if you take some random variable which is cumulatively distributed from any PDF, that variable will be randomly distributed from 0 to 1. And that is most important property, because you can use random number generator from 0 to 1 to generate some random number, which will be the random number on epsilon scale. And if you want to, if you see to which value of your random variable corresponds the value of a cumulative distribution, and that is the x value on x-axis, then you're pretty much sure that you used random number to generate a random variable which follows the probability density function from which the cumulative density function was derived. So that is maybe the most important thing in Monte Carlo, because now you have the method to randomly sample any random variable from any distribution. Okay, let's see some examples. The most, I will emphasize this on this slide, the exponential distribution. It is some function like in the lower left corner, and if you put this PDF into equation in upper right corner, you will get cumulative distribution. You can solve this integral, it's not so very hard, and then you can inversely derive the random variable x from a random variable xi, and you will get equation in the lower left corner. And that's the way how you are deriving random variables from any probability density function. This function has very important property in radiation transport, because this exponential function gives you, it is the PDF, probability distribution function of a free path. And the lambda parameter is actually the mean free path. So if you know the mean free path of your particle, then you can derive any free path just by using this distribution. Now we can, our starting problem make some more complicated. We had Brownian particle which we move in equidistant steps. Now we can introduce not equidistant steps, but free path. How? Because we know how to derive free path from main free path. And now, if you see the trajectory of our Brownian particle, if you replace the d, which was fixed in our first example, with the random variable generated from exponential distribution, then you will get some particular free path. And now you see the distances are not fixed, they are randomly sampled from our distribution that has physical meanings. It is a free path of particle. Okay, There are another methods to derive random variables. If, for example, this method of inverse function doesn't work, but I will skip these slides. I don't have time for everything. And it introduced now more dimensional problem. Suppose we don't want to stay in a plane. We want to go into space. So we need somehow to move particle not just in one plane, up, down, left, right. And how are we going to do that? We'll simplify and expand our problem. Instead of drawing circle, let's draw sphere around our particle and randomly generate point of sphere. How can we do that? Well, mathematics can be useful here also because all equations are easily solvable. And if we derive PDF of this distribution, how can we do that? We'll take a simple elementary surface on a sphere and divide it with the whole sphere, and you have a PDF of that function. And these equations are also solvable. And you can derive it in a second line. You see how can you randomly sample theta and phi using some random numbers, psi. We don't know yet how to generate random numbers. It will be soon enough. In the right corner, you see example of three-dimensional movement of a particle with a mean free path equals to 1. And in the lower part, in the lower left part, you see, let's say how many lines, 10, 12 lines of code, which is used to solve this whole problem. So it's not so complicated. You just need to know what to do. Random numbers. Let's see how can we derive random numbers. Simply as is, take a physical process that is fully random, repeat it many times, score the values, scaled from 0 to 1, and you have random numbers, true random numbers. But that's not going to work in simulation, because you need something that you can be reproduced with a computer. So we are taking something that we call pseudo-random numbers. It's not real numbers, because they are generating using the real algorithms. But if you take the sequence of these pseudo-random numbers and give it to somebody and tell him, okay, test me, are these real random numbers? He should not be able to say that, okay, this is not real numbers. If he says so, then your generator is not so good. Even though you have deterministic process of generating these numbers, they should be fully randomly generated in interval from 0 to 1. And Metropolis, this is a quote from a paper of Metropolis. How can you generate random numbers? The simplest maybe way is to show you is to take 6-digit number, square it, take 6 digits in the middle of new square number, and that's your first random number. Square it again, that's 6 digits in the middle. In the middle, you get a new random number. Repeat the process, and you get sequences of random numbers. Well, the problem with pseudo-random numbers is that they're repeating after some time. And the more code, the more algorithm, the better the algorithm is, that this period is longer. And now you can have algorithms that have a period of 10 to the power of 20 or something like that. So it's very good. You cannot exceed that period. And this is the example of a function that generates random number in one particular transport code. I said that I will not talk about code, so I will not mention the name of any code. I will do it in general. And you give to this algorithm two particular numbers, which you call a seed, and it repeatedly generates sequence of random numbers. So it is also, it maybe looks like complicated, but if you see there are only 10, 12 lines, so it should not be so complicated to understand. Okay, now let's go to a step further. All we did up to now is follow the trajectory of some random moving particle. But particle of transport or radiation, differs from that kind of random moving particle is because it exhibits interactions in each point of movement. So we need to know somehow to add interactions of our quantum radiation into the whole story. How can we do that? Okay, and there's another problem. In interaction, you can generate the new particles, which we call secondary particles. The one that created secondary is a primary particle. Each interaction is usually called event, and the whole track of particle is usually called history of a particle. So we have a problem. We need to add interaction, and we need to be aware that in that interaction we can generate new particles. Then we should somehow simulate the new particles also. To add event, we again need to know some mathematics and physics now. We need to know what is the most important property that is describe our type of interaction. And that is in most general form is a double differential cross-section, which gives you the probability of particle to lose some amount of energy and be scattered in some solid angle. And if you know this value, problem is pretty much done. The main problem is because in most of the cases you do not know the analytical form of this quantity for various types of interaction, and that is the biggest problem in Monte Carlo of transport radiation. Physics. Physics is the greatest problem because you do not know very precisely how things work. You don't know differential cross-sections. Some of cross-sections are gathered from experiments. Some cross-sections are made in some tables and you need to interpolate them. There are few examples, well, not just few, but there are more examples in cases when you don't know the exact value of cross-section than the cases you know the cross-sections. So if you know differential cross-section, you can derive total cross-section, and that is a very important property again, because it is related to a mean free path. Because if you know total cross-section, you can simply derive mean free path. And now we know cross-section, we know free path, we know how to distribute particle if it is random process, and we can do some simulation. But in some particular cases, due to interaction of our radiation with the material, scatter will not be always random. As in fact, in most cases, it will be some other distribution which is derived from physics of a particular scattering process. So let us take an example and suppose that we have two interaction mechanisms. So some particle can in some point exhibit two ways of interaction, not just one. And in nature, this number is very much higher. It's not just two. It is in some cases very, very high. And how can we now deal with these things? Then we need to know two differential cross-sections, and we can get two total cross-sections. If we sum them, we will get cross-section for A and B are called partial cross-sections, and from that we can derive total cross-sections, and from that we can derive main free path. Now we can sample particular free path in two ways: by sampling partial free paths and taking the shorter one, or we can derive probabilities of interaction A or B to happen. Just simplify, generate some random number, and you can choose the outcome of your event. And we get to the picture we saw in the first slide. How can we transport particles? We are in the luck because most of the processes in nature are Markovian type, which is very important because that means that the outcome of some interaction event doesn't, if process is Markov, doesn't depend on the past of histories of your particle. And that is very important because in any point of transporting radiation, you can stop that process. And later on, you can you can just move along and you will not insert any bias in your simulation. And this is important property because when you have complex materials, when radiation is not transported in just one material, but you have let's say, a surface that divides two kinds of materials, Markov processes allow us to do the following. Let's start from randomly generating trajectory of our particles. In each event, we simulate some kind of event. In that event, secondary particles could be generated. What are we going to do with them? Well, we take the properties of all these particles, store them in some variables, and save them for later on when the whole history of primary particle is finished. And when the particles come to some other material, to crossing surface of two materials, and that is not so hard thing to deal with because you just stop the particle at the crossing surface and just follow again transport of a particle with the characteristics of new material. Well, thanks to the Markov process, this is this situation with non-homogeneity of our material through our, we are transporting particle is maybe of great importance because Monte Carlo, because of that, can be used to solve problems in complex geometries. If you use analytical method, you will have a problem with boundaries if you have complex problems. This is not so great problem here. Okay, what are we going to do with secondary particles? Well, simply save them as primary particle history is finished and then treat them in the same manner as primary. And then you repeat that in circle. 25, just 2 more minutes. I will skip the method which is used to increase the uncertainty, to decrease uncertainty of some particular events, and goes to the okay, this is just example of okay, cross interaction cross section. For photon, the story is quite simple because there are not so many types of interaction, and photon, after exhibiting few contact scattering, usually be absorbed or creates a pair, so doesn't last anymore in your simulation. And to know that, you need to know differential cross-section of every type of interaction. From that, you can derive total cross-section. And think without electrons is similar, but there is a problem with electrons because they're charged. And they can have events, they can interact many times in very small step lengths. So it is very hard to simulate that kind of interaction because there are so many of them. So we, because of that, go to something that we call multiple scattering theories. Here is the example of how does the simulation of bunch of empty electrons looks in the water. Red lines are trajectories of electrons, and the yellow ones are secondary photons. And I will just glimpse of multiple scattering theories. If you want to transport your particle from starting to ending point, you can generate trajectory. You can do it several times and score all the final points and generate PDF from it. It will, in this case, be normal distribution. And then you don't need, again, to score all trajectories. You can just use this PDF to generate final point after some amount of step lengths. And what did you do? You condensed histories. And in this way, somehow, not simple as this is, their theory of multiple scatterings is implemented in a simulation of charged particles in radiation transport codes. And for the end, I will just show you one slide, which is my vision of most simplified algorithm for radiation transport. Start with the particles, generate next point of event, generate collision in that event, determine energy loss, are there secondaries created, or do the all things you need to do to follow the simulation. If the energy after that collision has again more energy, do it again until all energy is lost, then go to secondaries. When you exceed all that, go to the new history of primary particles. When you exceed that, your simulation is ended. Also my presentation. Thank you.
Thank you very much for this very nice introduction and very nice overview. Are there any questions? Is there one in the chat? Okay.
So Michael Womenchev asked, what is the difference between the random walks and the tracks in particle interacting with the medium?
Sorry, can you repeat? What is the difference between random walks?
And the tracks of particles interacting with the medium?
Well, when you have a random walk, you can just move particles whatever the medium is. If you have a medium, then you need to know mean free path of that particle in that medium. So it could be differences, but in general, there's no some great differences in that.
Okay, are there any questions? There's one question over here.
Yes, is it working? Okay, I have a question about random numbers. I've heard before, it's a long time ago, that there are some like part of computers developed by somebody, which are made from radionuclides, which gives you really random numbers. Is it working already, or is it already forgotten?
Is it already forgotten? I don't know, but that is the physical process that you can use to generate random numbers. Is this in use at the moment? I really don't know, because everybody uses pseudo-random numbers, so I cannot answer that question. Is somebody really using that maybe...
Oh, it's too slow. Oh, thank you very much. It was a long time ago I heard about it, so thank you.
Okay, so we had Chesk next to you.
Behind you.
Just a minor comment from the point of view of a developer. If you have a random number sequence that you cannot reproduce, imagine that your code crashes and you want to understand why. If you are not able to go again through the same steps, then you are in dire straits for debugging.
Yeah. Yes. So you can reproduce pseudo-random numbers with the same sequence if you start from initial same seeds.
Okay, thank you very much again, Vladimir.
Thank you, everybody.
And then we move to the next presentation by Carles Domingo on the unfolding of neutron spectra from bonosphere measurements. You will hear it.
Only the arrows, yeah? Okay, thank you. So, I want to say 2 or 3 things before starting the presentation itself. Is that, okay, this presentation is made after the results of the unfolding exercise of Working Group 6 has proposed. But I am not going to concentrate very much. Yeah, okay. I'm not going to concentrate very much in the exercise itself. I will take some of the conclusions at some time, okay? That's the first thing. The second thing is that I am not, I am going to concentrate much in the unfolding procedure, not in any particular unfolding code, okay? And as well, there are many experts in the audience, and there are probably many beginners in the audience. So sorry for boring the experts, and sorry probably for being, I don't know, I don't want to be very complicated for the beginners. So let's hope to make a half and half thing, okay? So the unfolding problem starts with the Bonner spheres spectrometer, and you probably all know the history of that. So it's starting on 1960 from a proposal, I mean from an article from Bramblett, Ewins, and Bonner, so who proposed the, to have the neutron spectrometry with a thermal detector in the center of a set of different spheres, which I will come back later to that. From a paper from 2004, David Thomas was already stating that among the available neutron spectrometry techniques, the Bonner sphere spectrometer is the most frequently used in radiation protection. And this is because it is able to cover about 10 to 12 energy decades in the energy of neutrons, from thermal to very fast or high energy neutrons. So let's go a little bit to try to center the problem we have when unfolding. So we have a given Bonner sphere spectrometer, a set of spheres of maybe different materials, originally polyethylene, but now for higher energy you need to put inserts of different materials in the spheres, and a thermal detector of whatever type in the middle. So the thermal neutrons reaching the central detector depend on the energy of the neutrons in the field and of the diameter and composition of the sphere, because thermalization for different sizes is different. So every sphere responds in a different way to the field of neutrons we are trying to measure. It is also important that when we measure with Bonner spheres, we have a somehow constant field, and we put the spheres sequentially. Only when fields are very big or they extend into a very big area, we can put simultaneously spheres to measure this field, as it is the case, for instance, for cosmic radiation neutrons, okay? The field of the neutrons produced in cosmic rays cover a huge area, so you can put several detectors with the approximation that the field is constant for all the detectors, okay? So now that the starting for, I mean, my students have always difficulties on understanding what I am going to say, okay? So the response of a given sphere to a monoenergetic neutron field can be calculated as the division of the measurement given by the sphere by the fluence of this monoenergetic field. And this is true for a given energy, so that's the response of the sphere to this particular energy. But real neutron spectra are far from being monoenergetic. As I said, they cover several decades of energy. That's okay, equilethargic representation of sample spectra obtained in radiotherapy rooms while the machine is treating, okay, not the patient, but a phantom, okay? So, okay, so we have to work a little bit more on that. And here is where my students come crazy. I mean, lowercase phi, bar phi, and uppercase phi. So, okay, that's a complete mess of everything. Okay, uppercase phi is the total fluence of the field. Lowercase phi subindex E is the energy distribution of the fluence, which represents the derivative of the fluence with respect to energy, okay? And then, if you take this distribution of fluence and you divide by the total fluence, you get the distribution of the unit fluence, okay? Which is this bar phi which appears there. So relations are written in there, and obviously the integral of the energy distribution of fluence is the total fluence, and the integral of the unit distribution of fluence is 1, okay? So then we can use the definition of response function that we said before, energy by energy, just to say that the reading of a given sphere is the convolution of the response function of this sphere for all energies and the energy distribution of the fluence. Perfect. So we reach the point. Right. But numerical methods do not allow us to work with continuous functions. When we calculate response functions, we do it in a given binning. So, okay, so we have to discretize that. So the immediate discretization of this equation is the one which is in the lower left corner. So it just taking boxes for the energy, taking bins for the energy, and changing the indexes instead of putting a continuous E variable, putting a subindex J just to calculate that. So the unfolding problem just reduces to having a set of measurements from a Bonnier sphere, I measurements from I spheres, deriving the fluence distribution in J bins. Okay, that's, I don't know, a simple problem or not, but the practice says, okay, that could be tricky, okay? We know we have generated by Monte Carlo, normally, the response functions of our set of spheres, normally known as response matrix, because we have I and J indexes to characterize them. So the unfolding process is then the process of, from N, knowing R, deriving phi. But which is the problem for that? Is that in normal situations, you have a limited number of spheres of the order of 10, 8, 12, that order, normally. And you have an energy binning covering these 12 decades of energies with at least 100 or 200 bins. So you have to solve 200 equations with 11, no, I'm saying it the other way, 10 equations with 200 unknowns. So it's clearly an underdetermined problem. So mathematically, there are infinite solutions to that, okay? So of these infinite solutions, only a few of them may have physical meaning. And that's the point for the unfolding, to get the solutions with physical meaning, okay? So you need something else, you need pre-information. And this pre-information you can give to the unfolding methodology, you can give basically from two different methods. One of them is knowing a gas spectrum similar to the one that you know that the place where you are measuring, there could be a spectrum similar to whatever. Or maybe you have all the information to make a Monte Carlo simulation for this spectrum. Then this is a good guess spectrum to start with the unfolding. And the other approach is knowing that in some situations, the physical form of the spectrum is characterized by a few parameters, maybe of the order as well as less maybe than the number of spheres. So then you can characterize a spectrum with these parameters, and then you can give a guess a spectrum from a parametrical mode, and then varying the parameters you will get that. So, okay. So that's the two approaches that different unfolding codes are using. Then it is important to know that, okay, so we have a few equations with a lot of unknowns, so we can try to increase the number of equations. So put more spheres. Okay, that probably will worsen the problem, okay? Because the results that you get from the different spheres are not completely independent one from the other. So if you have seen before the different response functions of the spheres, there are many places where these response functions intersect. So putting more spheres will mean that you will have more response function intersecting, and no new information will come out from there. So it is known that for, normal, calling normal the problem is not going up to higher energy, just to 20 MeV, okay? It is known that 4 or 5 spheres are enough if they are well distributed, if their response functions are well distributed to cover the whole energy range. More spheres will mean redundant information, and this redundant information, of course, can be used to detect maybe measuring mistakes, okay? So this is an example of a particular situation with the readings of the different spheres of a Bonner spectrometer as a function of the diameters of the spheres. And we see that they follow a more or less continuous distribution as a function of the diameter, and that somehow you can now think that if we put a sphere with a diameter between two of the spheres you already have, you will have the response, the number of count will be, okay, where the continuous line is saying. So no new information really, but in the example in the right bottom corner, you have an outlier there. You have one point which is clearly out of the path of the sphere, so you can detect that. So this is not really unfolding yet, just checking your data. So this is necessary, and this is a conclusion from the exercise, okay? You should check for the data to see if there are any outliers before unfolding. Because if you unfold that, you could get particularly bad results, okay? If more than one outlier is there, okay? So this is the general process of unfolding. You start in the upper left corner by a gas spectrum, parametric or whatever you have, a trial spectrum. Then you compare the counts that the spheres would give with this spectrum with the measured counts. You put an indicator of what here is called error signal. So if this difference between this trial and measure is small, then you may have finished. Normally it is not small when you start. So then you modify the trial spectrum and you give a trial solution as a restart of the process, and you start going around here. Okay, different types of codes use different methods to modify the trial spectrum, and even different codes also use different types of error signals or methods for stating when your unfolding is already finished or not. But basically, they are all the same, yeah, going around here. Now, once you get the solution from the unfolding, you get a mathematical solution, of course. It's probably perfect mathematically, but is it physically meaningful? And then here starts the user eye, or the user, I don't know how to say that, okay? The interaction with the user, okay? So, this is comments from David Thomas in 2004, okay? Unfolding codes are very complex. Very realistic a priori information is needed to derive physically acceptable solutions, okay? Expert users are needed, and in many cases, complex offline analysis is needed to get the uncertainties. Sorry. From this moment, okay, codes have been evolving, and at present, maybe there are more user-friendly codes than in 2004. In many cases, especially with parametric codes, very basic pre-information is enough to derive sufficiently accurate results, especially for radio protection, where the problems and the spectra we know that they are quite easily parameterizable, okay? We can parameterize these spectra, okay, in quite a convenient way. And some of them have now embedded uncertainty analysis. Going to pre-information again, unfolding with non-specific and educated default spectra may lead to absolutely incorrect results. So the default spectra is important. So this is nothing that I have said, it's something that Matske said already. Oh, sorry, that's not the year there, but I remember it's a quite old publication, okay? So normally unfolding will give you a correct value for the fluence. But if the pre-information is not complete, the distribution of the fluence will not be okay. And that means that when you go to calculate H star 10, for instance, radio protection quantities, you will not get the good result because the energy distribution is not right. So, okay, there are a few basic requirements about the pre-information, and this is also some lessons learned from the unfolding exercise. I mean, the components of the fluence cannot be negative. I mean, a fluence spectrum has no negative values, okay? If the radiation environment is known, then maybe you can put a lower limit and an upper limit for the energy of the neutrons that you are getting in the unfolding. thermal neutrons always appear with a Maxwellian distribution because they are thermalized from the primary neutrons that we have in the sources. For a radionuclide source with a scatter suppressed, there are techniques to suppress the scattering, no thermal neutrons should appear. I mean, thermal neutrons come from scattering, so, okay? And the final spectrum should be smooth if the gas spectrum is smooth. Unfolding by itself cannot put complicated structures in the spectrum. It does not have resolution to do that. If that happens, it might be that we are trying to minimize the difference between the folded counts from the unfolding process and the measured counts. If this is too small, then for making that small, maybe the unfolding process starts to vary in funny ways, the spectrum. So be careful, okay? Structures in the unfolded spectrum could only appear if they were in the gas spectrum, okay? If not, the unfolding process should not put extra structures in the spectrum. So I don't want to lose a lot of time on that, but it is just an example of how you can figure out a gas spectrum, okay? This is an example from the unfolding exercise where a pure parametric code was not able to reproduce the spectrum that was, I mean, the real spectrum that was provided, okay? So we can do different things here, is to use as much information as we have. So if we know that for a similar place, the higher energy part is whatever it is, and then we know from the parametric that the thermal has to be Maxwellian, and we can put a flat epithermal, we can combine all this information and make a gas spectrum to start with a new unfolding procedure, okay? And this is an example of how getting a gas spectrum in such a situation, okay? You can even go further than that, is, okay, the parametric mode of an unfolding process can give you good information, maybe, about the thermal and epithermal components, and the unfolding process will not, okay, should not change much the size, the form of a spectra, as I said before, but it is able to change the proportions of the thermal, epithermal, and fast components. So we can combine the output of a parametric mode unfolding for the thermal and epithermal, and with more information for the fast one. Take that as also a gas spectrum, and in this particular case, the results from gas spectrum 0 and gas spectrum 1 are here, compared to, this is the unfolding done with these two gas spectra and compared to the reference spectra, and in both cases, the result of the unfolding is close enough to the reference spectrum. So, just talking about the unfolding exercise, I want only to stress one thing there, is that there are basically, the participants here used 3 groups of unfolding codes, okay? The, let's say, codes from the fluid family, okay, parametric and also single gradient mode. The codes from the UMG, Maxat and Gravel family, and some of the users used self-made codes. And I only want to show the result of one of the exercises, where the results of the authors, of the, participants, are grouped by type of code they used, okay? And you see that independently of the type of code, there are results which agree with the reference solution and results which do not agree. So it's not the code, okay? So it's not the code. Maybe some particular self-made code that maybe, but I mean for the others it's not the code, okay? So after unfolding, please plot the unfolded spectrum. Unrealistic results are visible by eye. Folding the response matrix with the resulting spectrum and compare with the reference BSS counts. I mean, this is something needed, okay? Not only unfolding and that's it. So you have the response functions. Once you have your unfolded spectrum, see if you reproduce the counts. And compare literature for similar scenarios. So just let me put that as a summary of the exercise, and basically this is the summary from the EURADOS exercise. Amazing results used to be incorrect or inaccurate. So bear that in mind.
Thank you very much,
Normally, yeah. It's difficult to get the Nobel Prize, yeah.
Okay, now it's working.
Yeah, thank you very much for this talk. Just a little question about one thing. You said if one point is not, in the line of the other, you said you are to go to further investigations. Okay, I'm right. But in the literature, do you know some of this example? Maybe someone redo the measurement, it's different, or it's the same? And so what's happened? Is anyone do that and look at that?
Okay, probably if you have a result like that, you are not going to publish it. I mean, I can speak, I can speak for myself. I mean, many times I found outliers. So I normally repeat the measurement, and when I repeat the measurement, it's not an outlier. I mean, it's a mistake. The sphere was not well placed, or the detector had a failure, or something like that. That's the normal thing. I don't know from anybody that found such a discrepancy like that as a real case.
As you do the measurement in the with each Bonner spheres, one after the other, that means you can check that.
Yeah.
So if you check, it's different. Okay, you say, okay, it's different, so I will redo it, but immediately.
But if you have all together the spheres, then if you have something like that, suspect and try to make the unfolding without this sphere, and include afterwards this sphere as well in the unfolding, and see if what you get has sense or not, from the physical point of view.
I have a question. Thank you for this very clear and complete lecture about unfolding. I'm here, maybe I can go. I have a naive question for experimental physicists. If you want to make a measurement in a complex multi-particle field, is it possible to include the response function of the detector for other particles in the unfolding process? And do you have to know really precisely the spectrum, the fluence of all the other particles? Or is there a way to put it in the unfolding process and let the process try to separate the particle?
In principle, it is possible. I would say that it is difficult. Okay. First of all, you have to know very well the response of your detector to the different type of particles, and also take into account that it is not your bare detector detecting, I don't know, protons or photons or whatever. It is a complicated structure. So for mixed fields, it's a specific problem which needs investigation case by case.
Okay, thank you very much. So we have no questions from the online audience, so thank you very much, Carlos, again. And we go on to Rick Tanner, who will report about the intercomparisons in computational dosimetry.
Well, that's what I was just checking. That's a rare example of the audience looking more awake than the lecturer in this case. But yes, is that okay now? Yeah. Yes. Anyway, I was just starting off by commenting that the audience look very reassuringly more awake than the lecturer at the moment. So I've been given this task of reviewing the intercomparisons we've done on computational dosimetry over quite a long period, so it's quite a historical review. And I apologize to people who haven't acknowledged properly, because there are too many people involved to acknowledge everyone, and too many intercomparisons which will be done through Working Group 6 to include everything. I've probably concentrated on things that I have been involved with a bit more, because I have better access to the figures, and I actually understand the interpretation of it better. But so I'll start off with, this is work of many, many people, not just me. So that's not looking. Yes. So I'll give you a quick history of Working Group 6. We were actually one of the original working groups, and the only one that's still in existence in 1982. And it's quite interesting that back in 1982 they'd already identified computational dosimetry as one of the fundamental areas of research that should interest EURADOS. And it's only had 5 chairs over that period. I think Hans and I achieved the shortest terms of so far, and between Bernd Siebert and Gianfranco Gualdrini, who were 2 sort of giants in this field, they were actually the chair of this working group for a very long period and did an amazing job in setting up where we are now. So we've made major contributions to the EURADOS work program over 4 decades, and it's very refreshing at this meeting to see some fresh faces in the Working Group 6 meeting to try and keep this going. And again, I've emphasised that there are so many contributors, I can't list them all. I first attended a Working Group 6 meeting in 1994, quite a long time ago. Maria's uncle, who I'm sure is here, was already a well-established member of the working group, so I'm not the oldest. At that time, I was just a novice MCMP for a user, and there was not so many people doing Monte Carlo in EURADOS. So, if you admitted to being having some expertise, you found yourself in the working group. And at that time, basically, most of the Monte Carlo work was within the working group in EURADOS. But now, I believe every single working group is doing Monte Carlo in some capacity. So the area has developed hugely over these 40 years, and the 30 years I've been involved. Back when I started, many of the people doing the work for EURADOS had their own codes, which they'd originated themselves. They knew their code better than anyone knows the code they're using that they got off the shelf. But they were limited in scope, because if a person develops a code, you can't possibly commit. I remember a few years ago, someone from the MCMP team, and they at that stage had 1,400 man-years of effort going into programming it. No single user can do that unless they live to be very old. They also have a problem of tending to retire with the originator. But one of the things we really liked at that stage was the independence of the calculations. Now we get lots of correlated results because everyone's using MTMP or Fluker or JANT or EGGS. So now, I think in the working group, no one has actually been talking about their own code for quite a long time. Everyone uses I use the expression, all singing, all dancing codes we have today. But back then, MCMP didn't transport electrons. EGS, of course, was only photons and electrons, but also other codes like Fluker was certainly around, but not very easy to get hold of and use. JANT, I don't believe, was publicly available either. So quite big developments in that time. When I started, we were really struggling to do coupled calculations. Gianfranco Gualdrini had introduced, and his team in ENEA had introduced electron transport into MCMP, so there were some preliminary results where you could actually transport the electrons from a neutron or photon calculation, but it was still experimental. People tended to do their calculations on mainframe computers. Many of you probably haven't actually had the experience of submitting your job for your Monte Carlo and waiting for everybody else's calculations to finish before yours would even start. It was hard to get calculations to converge, especially for complex geometries. Back then, there was lots of discussion about variance reduction, how we could actually get a result out of our codes that actually meant something. Now I speak to younger scientists who do Monte Carlo, and they don't see the need for variance reduction. They can get convergence just setting up a problem, and it's fine. And we couldn't even load all the cross sections. We used group cross sections for less important elements and isotopes in the problem, and you just simply couldn't load everything, and certainly could not load Voxel Phantom at that stage. So obviously the merged phantoms, either the Adam and Eva, were being at that point replaced by Voxel Phantoms, and these developments have carried on since. And it goes blank. Yeah. So now I think everyone's using one of the major codes. You'll see that people tend to have control of their calculations using a PC, a laptop, or a PC cluster. And merged phantoms have become largely obsolete, and we've been moving now from voxel phantoms on the left here to the mesh phantoms, as already been mentioned. And people getting convergence on their problems is very rarely an issue now. They can run plenty of histories, except for the mesh phantoms. So in the last 10 years, we've done, in EURADOS, the intercomparisons of personal area dosimeters have become a core part of the work program. It's very much recognized in the strategic research agenda of EURADOS. It's a quote from the strategic research agenda, and it actually includes in the intercomparisons as one of our core activities computational dosimetry methods. So it's really recognized there. But the emphasis, the importance of the personal dosimeter and area dosimeter intercomparisons is partly due to accreditation as well. That I hope it's probably very hard to read. You'll be able to read it online. It's just a copy from the ISO 17025 standard, which basically emphasizes that to get accreditation, you need to do inter-laboratory comparisons, intra-laboratory comparisons, and proficiency testing to be considered to be competent. So now I've tried to distinguish two types of intercomparisons we do here as type 1 and type 2. I've just made those numbers up for this presentation. Where some of the problems, the working groups get together, people with different codes and different methods, to try and converge on the correct answer for a solution. We've done that quite a lot in working group 6 over the years. But others are the more standard intercomparisons where we define a problem and distribute it for anyone to have a go at it. That's what I'll be talking about mainly in this presentation. As far as I can tell, not just the first working group 6 intercomparison, but the first EURADOS intercomparison was probably also an unfolding exercise. I've got the reference for it. It's a PTB report there, and I probably could have asked Hans to get me a copy of the report. I haven't been able to obtain. It's not available online, the original report, but it was an unfolding exercise, a bit like Carlos has just been talking about, and that goes back to 1990, the report. So that was work performed in the 1980s. So with intercomparisons, type 1, we're trying to converge on an optimum solution. You're still never going to get the same answer from everyone. And then type 2, we compare submitted results with the, I put it in quotes, right answer. But what is the right answer? You can't do an intercomparison without comparing with something. Otherwise, you just present lots of data and say which ones are good enough, which ones are not good enough. In many of these, we compare with the author's solution. We're trying to emphasize it's not the right solution. They can't be sure it's even the best solution compared to some of those. We have got some very expert people taking part in comparisons. Sometimes a different code than used by the author might even be better for the problem. There'll be variation between the solutions that are not caused by mistakes. It's simple statistical variation, of course, different input data, different models, different codes. So, but then I've emphasized this bottom point. When we do a comparison, the problem solutions do stand out. You know when someone has done something seriously wrong, as you'll hopefully see. As I mentioned before, when I joined Working Group 6, we were actually, all the data had just about been generated. I didn't generate any of the data for ICRP 1996, ICRP 74, or ICRU 57. They're the same report. They were produced by EURADOS Working Group 6, and the data are still in use today. They will only become obsolete when the new ICRU 95 data become a part of the legislation. So, if you want the effective dose data in those reports are, of course, obsolete because ICRP have updated them, but the H*10, HP10, etc., the operational quantities are still what we use today. They were produced by this working group. This was like a type 1 into comparison in some respects. I'll just show you there. Those are the data for the female liver. You'll see that they took data from not just from within EURADOS. It was also collecting data from around the global community, and you'll see good agreement there for the conversion coefficient for neutrons for the female liver. From our lat is from the right lateral exposure. That's so clearly we could do good Monte Carlo, and those data gave good agreement. One of the problems was actually less the Monte Carlo than the descriptions of the Murd phantom. Everyone had to set up the Murd phantoms differently. So you see that these are the data that were used for the conversion coefficient for neutrons for the male colon from the right, and there's a big scatter in the data. And within the working group, I remember long discussions about how do we come up with something that's the best fit to this. And this is an example of where Bent Siebert had a complicated mathematical way of doing this. He came up with the line there, which is considered the best fit, but you'll see that there was still big scatter about those data. Some other examples from ICR for those reports, you'll see the electrons and neutrons, there was quite a big scatter in terms of, these are quite expanded scales. On the left, you've got the electron conversion coefficients for different energies for, unfortunately, I think you can see, I can't see it on my screen, the y-axis title. For the skin dose quantities, and then H*10 for neutrons in the middle, where they've done a fit to it, and then you see still scatters of 10% or so around those data, and for electrons on the right for H' 0.07. So there was quite a bit of uncertainty in those data. But then the first big intercomparison that Working Group 6 did was a thing called QUADOS, Quality Assurance of Computational Tools for Dosimetry. It was the first large-scale intercomparison open for participants anywhere in the world. We produced a set of 8 problems, and here one of the first issues you have with intercomparisons is can you define it in a way that everyone understands what it is, how to set it up. In those days, as I've highlighted, people could not do problems with a massive CPU requirement. No one is going to spend weeks setting up a problem for an intercomparison. But you do need this rigorous, unambiguous specification of the problems, because otherwise people do make simple mistakes. This was concerted action of the European Commission. It was an intercomparison aimed at evaluating the computational codes for dissymmetry in radiation protection and medical physics. So this was quite a big piece of work. These were the objectives of it: to provide a snapshot of the methods and codes, furnish information on the method to use to assess the reliability of computational results, and disseminate good practice through. And this is one of the fundamentals in intercomparison, is try and disseminate good practice. And also give people the chance to quality assure their procedures, which is, again, when you see some of the results, and if you've seen some results from Carles there, an important outcome, hopefully, of these, but also uncertainties. Reporting a result with no uncertainty and not considering whether it's a valid result or not is pretty common, and unfortunately, in scientific publications when you referee. Oh, damn, I've gone. Yeah. One of the things we've always had to try and emphasize, we're not going to say this code is bad, that code is good. That we never intend to do that. We cannot conclude that the code is at fault. It's probably the user, and if you've used a code that's not appropriate for the problem, then you should have known. So it was intended as a comparison of usage, as in all these intercomparisons, and we have to normalize the solutions normally to the author's result. And we at no point try and imply that the author's got the right result. You can't, when you see the results, you can't use an average of the results either. That's just not practical. These were the set of 8. Quite a broad distribution of problems. I've underlined the one in the middle because that's the one I was responsible for, and that's the one I've got easiest access to the data for. So that's the one I'll concentrate on a bit in this presentation. But we basically had some medical problems. The first 3 essentially medical. They have to be fairly easy to set up. Some of them are to do with calibration issues, phantom backscatter, calibration fields for neutrons, germanium detector pulse height distribution PhD, and a simplified helium-3 instrument calibration system. So they were all, none of these required too much effort. This goes online, so you can look up these references. But we summarised these outcomes in 2 papers. One about neutrons and uncertainties, and the other one about pitfalls and modelling inconsistencies. So that those are, if you've got access to radiation protection dissymmetry, easy to get hold of. Oh, have I gone too far? Yeah. So. I'm going to concentrate on the one that I set and analysed, just to give you an idea of how things went. This is not a very easy diagram to understand. The dark blue is water, and the magenta colour is a perspex shell for a phantom. The phantom is much bigger than that. It's just a close up of the phantom. And then the thing on the front there, the turquoise is the holder of an albedo dosimeter. The little orange bits are the TL material, it's that thermal material, and in an aluminium card. So what it does is you've either got the direct neutrons detected, which is with the top element there, or the albedo detected, which is the bottom one. And if you look at the cross sections at top right, this works because lithium-6 has a very high thermal neutron capture cross-section. So that's the fundamental mechanism by which you're detecting things. So it's about counting the number of lithium-6 captures, essentially, to get the response. We got 17 solutions, one of which was deterministic. I think probably about the last time we got a deterministic solution in one of intercomparisons. I may be wrong there. Because this was a photon and a neutron problem, not everyone did the neutrons, not everyone did the photons. But basically, we got solutions from around the world, as far as 3 from the US, South America. This was written before EU expansion, I think. So I don't think some of the countries from Eastern Europe were actually in EU at that time. So this breakdown is not really relevant. So So here we've got, just to show you how bad things get. The ones in the middle in black, I've not highlighted. You can't possibly label them on this display. Note it's a log scale on the left, so you've got two results which are way too high, and also not. If it was just a normalization problem, they'd be high by a fixed amount, but they're not. It's problem 4, and the letter just denotes the participant. And then there's 3 which are way too low. Some of these are made clear material specification problems, but they are. We never got to the root of why some of these have got such bad results. But you see that's down a factor of almost 1,000 too low, up to a factor of almost 1,000 too high, and this does matter. So that's all solutions. So and then just these are the ones in black on the original on the left-hand side. So this is just the better solution, but you still see some non-statistical variations there. I've left the ones in black which we considered to be fine and within statistical uncertainties of my solution and one another. But you still got the deterministic solution is labelled NA and ND, so it did actually pretty well. But you wouldn't. It's not surprising it doesn't get the exact right result. But there's still some problems. Quite how solution J managed to go over and then under different energies is a mystery. And I think at the top end, I should have not gone quite so close to the edge of the slide. Different cross-section libraries did cause a variation for the highest energies, which wasn't a user issue. Overall, and I can't possibly, I haven't got access to all of the slides properly. Some people, I know Paolo was involved in this, and I'm sure that others in the room were also involved. But the general conclusions for the whole thing was that we got a good set of solutions. About 80 people took part in the intercomparison overall, across all the problems. Not many. I don't think anyone attempted all the problems. MCMP was already quite dominant back then. In actual fact, most solutions actually did agree with the author solution across all the problem sets, and there was generally good agreement. But there were some large systematic errors, as I say, up to a factor of 1,000. And many of the participants needed substantial help to improve their solutions and get good agreement. Most people quoted statistical uncertainties, which is important, but there was still very little consideration of uncertainty. But then we did another in the sort of Conrad period, another set of intercomparisons. But just to confuse everyone, Working Group 6 became Work Package 4 of Conrad. You'll see on the left are the full members of the group who actually coordinated this. I've got myself down as HPA there, one of our many name changes, but again, this was coordinated by Gianfranco Guardrini at this stage. Ben Siebert stepped down from being the chair, and there were a set of more demanding problems, which are listed on the right. But already, Working Group 6, I'll call it, but Work Package 4, Computational Dissymmetry, was getting formal relations with other working groups. So with Working Group 5, which is now Work Package 5, which is now Working Group 7, on internal dissymmetry in a collaboration on a knee phantom, Monte Carlo. Work Package 6, which is now Working Group 11, on complex radiation fields, and also Work Package 7, which I think is that's now what is Working Group 9. So we had those formal collaborations set up, doing sort of type 1 type of intercomparisons. But our the formal part of the program was to do another intercomparison with 8 standard problems with experimental data this time, unlike the previous one. So this is one that Paolo was involved with on a bonosphere spectrometer, which Carl has been describing. And certainly in the first set of intercomparisons. We never had anything quite as complicated to set up in terms of geometry, and it's about simulating a set of Bonner spheres using Monte Carlo. You'll see there's, it was a limited set of spheres, but you've got one with a lead insert as well, which is the largest, the 12-inch sphere with a lead insert to boost the high energy response. So it was a more, yeah. So there's a massive set of results for this. But you'll see that compared to what I showed you just now for the previous comparison, there's pretty good simulation of the Bonner spheres, and clearly not everyone could do the largest spheres. So some of the data sets stop short. And in terms of what impact it has on the unfolding, you see the results on the right, and it's not too dramatic an effect. So basically, I think you've still got some pretty poor results. You'll see the orange diamonds very low, and then for thermals and very high energies. But you did get generally good agreement. I sort of inherited the problem of doing P3. I should have checked with Mikhail exactly what the status of the Sigma facility at Cadarache is. But at the time, it had 6 americium beryllium sources in it. Veronique Lacoste from IRSM was going to do this, run this problem, but she, I think, left on maternity leave, if I recall, and I ended up doing it, leading for this one. So we're relying heavily on information provided by Veronique. So basically, you've got 6 large americium beryllium sources. I think it's probably californium now, so this is historic, in a large graphite block to get a thermalized field. You can see an instrument being calibrated there in one of the reference points. So it's quite a big geometry and a lot of scattering. You've got to get your thermal neutron scattering correct. Now, you see, the left-hand figure is the total fluence calculated by the participants. And the right-hand figure is the H-star 10 calculated by the participants. This is normalized to my solution. And of course, as the author, I was going to spend much longer on getting my solution right than any of the participants, I suspect. You'll notice the green value and the broken y-axis. That was just a normalization issue. One of the participants had got the normalization wrong, so came in and reported a result that was a factor of 70 too high, 70 or 80 in terms of H-star 10. But with some discussion, managed to get the right result and resubmit it. That's why there's 2 points for the green data. Generally, when you do these in comparison, it's reassuring when you get quite a few people with I do need to go quite fast, with results that are consistent with your own, because you do have some confidence in your reference solution at that point, but there's still big deviations. It's not so bad from the underestimates there, because I've only got that break in the axis above 1. Yeah. Sorry. No. Yeah. And here we also did HP10 and actually simulating this directly in a phantom. And again, you see quite a scatter on the results. But I realise that the time is getting a bit short.
Well, it's actually up.
Is it? Yes. Yeah. Sorry, I've been talking too. So to conclude, this was a much more demanding set of problems. We asked people to do things they couldn't possibly have done at the time of the previous comparison. Still, MCMP was very dominant, but we still had some very poor solutions. But every problem could be solved by some of the participants. Now, in this presentation, I haven't actually gone into some of the significant cross-working with other working groups. And Thomas is here. We did a lot of work on the knee phantom with working group 7 and also working group 11 on high energy fields. I also need to, if you can download this free from the EURADOS website, the LINAC modeling, which was a very interesting problem set, which took a long time to publish because of staff leaving the group. But here you'll see that it was calculating in homogeneous phantoms the dose distribution from a LINAC. So you see there the scatter is pretty good. That's a very expanded scale to what I was showing earlier. That's just about mainly within about 1% of the reference solution. We've been running another set of intercomparisons recently.
Sorry, I think we have to stop here. Otherwise, you're preventing people from taking their coffee, which might be dangerous for the other speakers. It'll go on the website, but the recent set of intercomparisons we've done is just about to be published as a special edition of radiation measurements. So you'll see all the papers are in there on the unfolding that Carl is talking about, lots of micro nanodosimetry, fetal dose in proton therapy, and also the voxel phantom problems. Should I? No, I think we should stop.
Yes.
So.
Sorry. Yes. Sorry.
Yes. Sorry for intervening like that, but I think we should leave time, give the opportunity for one or two quick questions, if there are any. Okay, no one is daring. Okay, so the obvious question is, where's coffee? I suppose it would be up in the back. So we are now having our coffee break, and we start again at 11:30. Thank you very much.